Okay, so now I've rewritten up what we just talked about. This is the ways that I can choose little n balls from a collection of big N balls where order matters. And then this is the possible ways to choose it when ordering doesn't matter. All right, now what we want to do is we want to think about something that's a little bit like the binomial distribution. It's called the hypergeometric distribution. And it's the same where the binomial was choosing with replacement from a bag. So let's say we have big G plus big G green balls and big B blue balls. So these are green and these are blue. And we sum to capital N. So if I choose with replacement, the binomial said that the probability that I get little g green and big and little b blue with g plus b equal to little n was equal to what? Well, it's n choose g times the probability of getting a green ball, which is big G over n to the g, and the probability of getting a blue ball, which is big B over n to the b. And I can rewrite that in a rather suggestive way, you'll see in a second. G, and let's write this as G to the G, B to the B, over, well now this is n to the G times n to the B, which is n to the little n. Alright, now this was with replacement. Now let's do without replacement. Alright, if I do this without replacement, then what am I doing? Well, let's count the number of ways that I could do this. So first, let's just think about drawing the sequence where I draw all my green balls, and then, so I draw up to, so I have G green balls, and then I'm going to draw B blue balls, so I'm going to have little boxes. Okay? So how many different ways are there to do that? Well, for the first box, I have G choices for that balls for that one. The second blue box, I have G minus 1 choices. So that's just G choose little g. That's G times G minus 1 all the way down to capital G minus little g plus 1. And then the ways to draw the blue balls is B little b. And now if I forget about the colors and I just ask how many total ways were there to draw ones out, there are n little n. Now, the thing that I don't care about is I'm not going to require that all the green balls are right in a row and that all the blue balls are right in a row. So I'm allowed to shuffle these around. So think about having these G green balls and these B blue balls. And now I'm going to put the green balls in this bucket in any way I want. And they all have this same probability, I claim. And how many different ways are there to do that? Well, that's just n choose g. So this is the hypergeometric probability, which corresponds to the binomial probability. This is again in the hypergeometric setting. Let me just draw this, erase this picture here. This is the probability of G green, B blue, with G plus B equal little n, from this collection of capital G green and capital B blue summing to big N. This is doing it without replacement. And you notice the way we've written it, we've chosen this notation to make it look very much like the binomial probability, which has replacement. So this is without replacement, the hypergeometric, and this is without replacement. This is without replacement, the hypergeometric, and this is with replacement, the binomial. Okay, I want to make one last comment. So when I need to remind ourselves of the setting, we have capital G green balls, capital B blue balls, with the sum of G plus B equal to N. And we want to think about the probability of drawing out little g green balls and little b blue balls, where little g plus little b is equal to little n. And I want to do it without replacement and with replacement. This is the binomial, and this is the hypergeometric. Now, what happens as n goes to infinity, but little n, little g, and little b stay fixed? Well, as n gets very large, it makes sense that the probabilities don't change that much by taking a few balls out. So these two distributions should converge to each other. Let's see that. Well, let's see that by rewriting this distribution in such a way that when n gets big, it converges to that one. So the first fundamental thing to notice is that if I look at capital N choose over little n, and I compare that to big N to the n, well, this is capital N minus 1, all the way down to capital N minus little n plus 1, and I'm dividing that by n, and I have little n of them. So I'm going to split them up, each putting them over a little n. So this first one is 1, but the second one is 1 minus 1 over n, and all the way down to 1 minus n minus 1 over n. And notice that in each of these factors, as n gets big, but little n stays fixed, each of these factors goes to 1. So this converges to 1 as big N goes to infinity, while keeping little n fixed. So using that, let's see what we can do. So we're going to rewrite, we just keep the factor in the front, which is the same for both of them. Now this one, I'm going to write it as g over g, g to the g, and then I get a g to the g. That just cancels with that. And now I have a factor b to the b over b raised to the bth power, and then to kill that I put a factor of b to the b here. And now I do the same thing down here. I put an n to the n, but I divide it by n to the n, like that. And now if you think about flipping that up, that ends up in the denominator down here is n to the n. So this is exactly what I have for the binomial. And now notice that each of these factors, by this reasoning, go to 1 as I take, so this goes to 1, this goes to 1, as I take n equal to capital G plus little b to infinity, while if I keep, as long as I keep g to the n and b to the n constant. So I keep the ratios the same so that this part stays the same, and if I do that, taking n to infinity forces me to take g to infinity and forces me to take b to infinity. As long as I keep this fraction equal to p, let's call it, the success probability, and this is equal to q, the failure probability. As long as I keep these numbers constant, as I take n to infinity here, I have to take g, capital G and capital B to infinity, and then each of these terms converges to 1, and we see that the hypergeometric gets very close to the binomial.